morning, everyone, and welcome to the last day of our lab together. It's been a fun semester. Today we'll be starting. I'm Jonathan Dupree. I'll be your Toastmaster, and we will be starting off with Skylar Gray, and she will be giving us her 6-minute talk presentation.
Hello, everyone. Today I'll be presenting the role of thermodynamics in the formation of stars and galaxies. We'll look at how basic thermodynamic principles like heating, cooling, pressure, and equilibrium shape the structure and evolution of the universe. When we talk about stars and galaxies forming, we often imagine gravity as the main driver. While gravity initiates collapse, thermodynamics determines everything that happens afterward. According to NASA's star formation data, stars and galaxies begin inside vast clouds of cold gas. Thermodynamics explains whether that gas can cool enough to collapse, and how pressure pushes back against gravity, and how energy flows through the cloud. So the major idea throughout this presentation is that gravity provides the pull, but thermodynamics decides the fate of material. So up here there's a diagram of the cold cloud showing regions collapsing, which starts the formation of a star. Stars form inside extremely cold molecular clouds, some of the coldest regions in the universe. Whether a cloud collapses depends on something called the Jeans criterion. And the Jeans mass equation on screen shows that collapse happens only if the actual mass of the cloud is greater than the Jeans mass. Lower temperature and higher densities make collapse easier because they reduce the internal gas pressure resisting gravity. So this equation shows how thermodynamic properties, temperature, density, and particle mass determine whether a cloud stays stable or begins forming a star. Once collapse begins, gravitational energy doesn't just disappear, it transforms into internal thermal energy. NASA's protostar fact sheet explains that as the cloud contracts, the core heats up dramatically. The Virial theorem, right there, 2K plus U equals 0, tells us that during collapse, half of the gravitational potential energy essentially becomes thermal energy. This built-up heat makes the protostar glow even before fusion begins. So this early stage of star formation is almost entirely driven by thermodynamic heating from gravitational compression. Eventually, the protostar gets hot enough, around 10 million Kelvin, for hydrogen fusion to ignite at its center. Once fusion starts, the star must achieve hydrostatic equilibrium, shown in the equation on the screen for hydrostatic equilibrium. So, gravity pulls inward and thermal pressure from fusion pushes outward. That balance determines the size, the shape, and the lifespan of stars. So thermodynamics doesn't just start a star, it stabilizes it for millions or billions of years. Thermodynamics plays a major role on the large galactic scale too. According to NASA, gas falling into dark matter halos heats up through shock waves. This shock heating raises the temperature so much that the gas must cool before any new stars can form. NASA observations from 2013 also show that warm gas can shut down star formation entirely. The shock heating equations here describe how temperature jumps across a shock front. So galaxies regulate themselves through cycles of heating, cooling, and turbulence, all governed by thermodynamics. And just to explain the picture, that's the baryonic cycle showing gas, creating gas right here, shock heating a galaxy halo. These same thermodynamic principles have real engineering value. NASA simulations of galaxy formation use advanced models of turbulence, shock heating, and radiator cooling. These algorithms have contributed to better computational fluid dynamic modeling in aerospace and energy industries. Spacecrafts also rely on radiative heat transfer models inspired by stellar plasma behavior. Fusion energy research directly uses the same principles that stabilize stars, and cryogenic engineering parallels the cooling process seen in molecular clouds. So astrophysical thermodynamics isn't just theoretical, it informs engineering design on Earth. And I chose to show out images of the tokamak fusion test reactor at Princeton University. And this is what it looks like on the inside. And yeah, So that should be useful for future knowledge about stars. So to summarize, thermodynamics plays a central role in every step of star and galaxy formation. It determines whether a gas cloud collapses, how a protostar heats up, when fusion begins, how stars are supported, and how galaxies regulate their star formation over time. These same principles find practical use in engineering fields like fluid dynamics, cryogenics, and spacecraft design. Understanding the thermodynamics of the universe helps us understand both cosmic evolution and advanced engineering on Earth. Any questions?